This is a 555 timer. It's introduced in 1971. So some people may think that it's obsolete, inaccurate, or incompatible with modern electronics, but this is not true. It's versatile and it's still used by hobbyists and professionals. This video is not about the IC itself or its inner structure or other trite stuff, but in this video we are going to dive into the application of this cute IC and explore 6 projects based on 555 timers, from a simple blinking LED to modulating infrared rays, object detection on garage doors in fact, or making reciprocating mechanisms. Actually, we are going to see what we can make using this IC and how it can help us make awesome things. By the way, we will learn 3 modes of operation of this cute IC in the heart of 6 simple projects. I promise it's worth your time to watch it till the very end. Suppose that we have something that has to turn on and off periodically, like a siren, a warning light, whatever. How do you make it? I know the first application of 555 timers is so predictable. I guess most of you know what I'm going to describe. Application number 1, making a blinking LED. One of the most popular application of 555 timers is to use them to make a blinking LED. I call it a Hello World project for 555 timers. It can be used to indicate a certain situation in a project, like caution or danger. By the way, you can replace the LED with a relay to use the circuit to turn on and off almost everything. Anyway, let's dive into the world of 555 timers. This is the simplest circuit to make a blinking LED using 555 timers. Just connect pin 4 and pin 8 to VCC, connect pin 1 to ground, connect pin 2 to pin 6, place a capacitor here at pin 5 like this, place another capacitor between pin 1 and pin 2, place a resistor between pin 6 and pin 7, and place another resistor between pin 7 and pin 8. Then the IC will generate pulses to blink the LED at pin 3. 555 timers typically operate within a voltage range of 4.5 volts to 15 volts. However, it's worth noting that there are variations and different specifications based on the manufacturer and specific model. Always refer to the datasheet for precise information. Anyway, I'm going to set up this circuit and test it. As you can see, the LED is blinking. You can change the duration of on time and off time of the LED by changing the value of R1 and R2 resistors and the C capacitor. These are formulas for determining the exact on and off times, but there is an important point here. You may use these formulas for determining on time and off time, but you should expect different on time and off time than the values provided by these formulas because of the tolerance of the external components. This is the disadvantage of 555 timers. Its accuracy depends strongly on tolerance of its external components. Anyway, when the IC is repeating pulse generation, for example, making an LED turn on and off periodically and automatically, it's operating in astable mode. Application of astable mode is not limited to a blinking LED. You can imagine plenty of other applications, for example, generating sounds. Application number 2, making sounds. Humans can detect sounds in a frequency range up to 20 kHz. 555 timers can generate pulses up to 2 MHz. So it should be very easy to generate human audible sounds using 555 timers. Let's make it. The principles are the same as the blinking LED, but we have to increase the frequency. I think 5 kHz will be a good choice. 5 kilohertz means that there are 5,000 pulses in a second. Each pulse has to be 200 microseconds. I mean, the on time plus the off time have to be equal to 200 microseconds. This 200 microsecond is the signal period. From the definition of period, we know that T1 plus T2 is equal to the period. So T1 plus T2 is equal to 200 microseconds. By replacing the T1 value and T2 value, I got this equation. By assigning 22 nanofarad to capacitor C, I got this equation where R1 plus 2 times R2 is equal to 13,118 ohms. Here I have chosen 560 ohm for R1, so R2 has to be 6.28 kilo ohms. I haven't 6.28 kilo ohm resistor in my workshop, so I'm going to make it by using other values. As you can see, the output frequency is around 6.9 kilohertz because of tolerance of the external component values. Anyway, this frequency is okay for now. If I connect the speaker like this to the output, we can hear the sound. Here. This is the beep sound around 6.9 kilohertz coming out of the speaker. We can produce plenty of frequencies at output or even play music just by changing the value of external components. You can make even more interesting things using a speaker and a 555 timer in astable mode, something like police siren, ultrasonic, pest, animal repellent, metronome, etc., just by changing the frequency. Anyway, the application of 555 timer in astable mode is not finished yet. You can make a garage door sensor using 555 timer in astable mode. How it is possible, I will explain. But before that, I want to introduce the sponsor of this video, PCBWay.com. I'm proud to introduce PCBWay because they are professionals in manufacturing PCBs and offer a wide range of services, including PCB prototyping, CNC machining, 3D printing, and more. I'm using their services right now and I'm enjoying the high quality services at reasonable prices. Submitting order on their website is simple. You just need to sign up, fill out this form, wait for the invoice, pay the invoice, and then it's done. Your parcel is on its way to your address. That's simple. Anyway, let's move on to the next application. Application number 3, garage door sensors. What is a garage door sensor? A garage door sensor is a safety device installed on automatic garage doors to prevent accidents and ensure safe operation. The garage door sensor consists of two main parts, a transmitter and a receiver. Typically, they are installed on the opposite sides of the garage door near the floor. The transmitter emits an infrared beam across the door, and the receiver detects the signal transmitted by the transmitter. When the garage door is closing and the beam is interrupted by an object, a person, pet, or vehicle, the receiver detects the interruption and signals the garage door opener to stop and reverse its movement, preventing the door from closing on the object. This helps to prevent accident and damage to people, pet, property, or vehicles. Here we have an infrared transmitter diode on one side of the door that emits invisible infrared beams, and there is an infrared receiver diode on the other side of the door. When an object blocks the beam transmitted by the transmitter, the receiver detects the interruption. The concept is really simple, but you may wonder what it has to do with 555 timers. Let me explain. This is an infrared generating diode. It works just like an ordinary LED. If I apply voltage to its leads, it starts generating infrared beams. And this is an infrared receiver diode. When the infrared light hits this receiver, the receiver diode detects the infrared light and converts it into an electrical signal which can be processed by electronic circuits or devices. Let me test it. As you can see, in a normal situation, the resistance across this receiver is 2.5 kilo ohms, but when an obstacle interrupts the light, the resistance across this receiver reaches 26 kilo ohms. But this is not enough to make a garage door sensor because there are plenty of infrared emitting sources in the environment: sunlight, light bulbs, fluorescent lamps, and almost anything that creates heat, like your car or even your body. The receiver just receives the aggregate of all infrared lights, no matter who the transmitter is. If the system relies on the existence or level of the infrared light in the environment, it will not work properly, because when the light emitted from the transmitter is blocked by an object, the receiver will still sense the infrared light from other sources and it will fail to detect the interruption. So we have to think of other solution. What if the transmitter blinks instead of generating solid infrared light? I think it should work, because natural infrared sources in the environment are generating solid infrared light, and if the intended transmitter generates pulses, it should be distinguishable. The transmitter circuit has to generate pulses, and receiver circuit has to detect the specific frequency generated by the transmitter. So the transmitter and the receiver must agree on a specific frequency. 38 kHz is a popular and widely used frequency for infrared communication, meaning that the transmitter is blinking 38,000 times per second. Here is where the 555 timer comes into play. We have to configure the 555 timer to generate 38,000 pulses per second and build another circuit at the receiver to detect that specific frequency. Generating 38 kHz signal at the transmitter is a piece of cake using 555 timers. The big problem is the receiver. We need a complicated amplification and filtering circuit at the receiver to detect the 38 kHz signal in the environment, which is not subject of this video. But there is a simple way to bypass the complicated process of designing receiver circuit. It's to use a 3-pin infrared sensor. These 2-pin receivers can only sense the intensity of infrared light in the environment, but these are 3-pin receivers that detect the existence of 38 kHz infrared frequency in the environment. All the amplification and filtering circuitry needed to detect the 38 kHz signal is integrated into this IC. It is simple to use. You just need to apply the proper supply voltage to its VCC and ground terminals, and then it's done, and the circuit is ready to use. On the transmitter side, we just need to set up a stable mode 555 timer and set R1, R2, and C values to achieve a 38 kHz signal. One simple way is to use a potentiometer instead of R1 and adjust the potentiometer to find the 38 kHz signal. This is the transmitter circuit and this is the receiver. I'm going to set up these circuits and test them. I can adjust the potentiometer while measuring the output frequency by using the frequency meter capability of my multimeter to find the 38 kHz signal. As you can see, the output frequency is about 38 kHz. Now is the time to place this infrared transmitter at the output of 555 timer here at pin 3. Now the transmitter is emitting 38 kHz infrared signal and the receiver receives that and turns this LED on, meaning that the 38 kHz signal is hitting the sensor. When an object interrupts the 38 kHz signal, look, this LED will be turned off by the sensor. The circuit acts like a remote controller. When the transmitter sends a 38 kHz signal, the LED turns on from a distance. That's awesome. Also, this sensor can be used in many other applications, like what? Application number 4, data transmission. When the transmitter generates a 38 kHz signal, the LED turns on at another circuit, and when the transmitter stops generating a 38 kHz signal, the LED turns off. This is enough for transmitting any type of data, commands, sensor values, or even sounds and images. I'm going to connect the push button to pin 4 of the 555 timer like this instead of connecting it directly to the VCC. By pushing this button, the 555 timer is activated and it starts to send a 38 kHz signal. Consequently, the receiver receives the 38 kHz signal and activates the LED. Actually, this structure forms a remote controller or even a data line. You can apply a serial data signal like this to enable pin of 555 timer, and then you will get the same data signal at the output pin of the receiver from a distance. You can send almost everything. 555 timers are analog in nature, but they can be used in digital circuits. Anyway, the application of generating uninterrupted pulses does not end here. There are endless other usages. Generating PWM is a nice example. PWM is used in many control tasks. However, for sensitive control tasks, it's better to use more precise devices like microcontrollers to generate control pulses. Anyway, the next application of 555 timers is when we need to turn something on manually, but after a certain amount of time, it should get turned off automatically. Application number 5, ventilation. No matter where you are going to ventilate, a bathroom, a kitchen, a greenhouse, an attic, anywhere, you can employ a tiny and cheap 555 timer in its monostable mode. What's the monostable mode? Let me explain. The second mode of operation of 555 timers is monostable mode. In monostable mode, the 555 timer generates only one pulse when pin 2 is triggered using this button. The width of this pulse depends on the value of this resistor and capacitance of this capacitor, and it's calculable using this formula. For example, by assigning 100 microfarad to capacitor and 27 kilo ohms to the resistor, the T has to be 2.7 seconds. As you can see, by pressing this button, the LED turns on for 2.7 seconds. However, there may be some errors because of the tolerance of the external components. The pulse width in the previous example can be increased up to several minutes by choosing proper values for the resistor and the capacitor. This mode of operation of 555 timers can be used in many other applications. If you have an idea about this mode of operation, please share it in the comment section below. Anyway, let's move on to the last application. Application number 6, direction keys. In some projects, you may reach a point where you need two separate signals to change the state of the system. For example, when you need a reciprocating mechanism. In such a case, you can use a 555 timer that is configured to operate in bistable mode. This is the simplest bistable operation mode of 555 timers. Here we have two push buttons. The first one is to activate the LED at the output, and the second one is to deactivate the LED at the output. When I press this button, the LED at the output turns on, and by pressing the other button, the LED turns off. By using this simple circuit instead of the LED circuit, we can make a back and forth movement using a single DC motor. Look here, there is a relay here. Actually, it's a two-contact relay. The component is this. It has 8 pins. The relay pins are connected to the motor and supply voltages in this way. By using limit switches like this instead of these push buttons, you can make electrical back and forth mechanism using 555 timer. When the moving part of the machinery hits this limit switch, it will cause the switch to reverse the motor and invert the moving part direction. After that, the moving part will be in the way of hitting the second limit switch. The back and forth mechanism was the last example in this video, but there are plenty of other applications of this tiny, cheap and flexible IC that you can learn and explore. Anyway, we have reached the final moments of this video. I hope you enjoyed this video and learned something new. Thanks for watching. If you enjoyed this video, please give me a thumbs up, and if you like this video, make sure to subscribe for more.